chemistry, and also physics as well, so biophysical concepts. So in that sense, chemistry is unique because it's able to pull together different aspects of sciences together to make a subject. And there's lots of common mistakes that a lot of students make. I've heard a lot of students say that they found it one of the hardest of the three sciences to study. But if you follow the key rules to chemistry, you find that it's actually very straightforward. So there's obviously different syllabus statements that give a basic overview of chemistry, but in general, chemistry relates to properties of elements, compounds, and mixtures, and we're applying this to scientific models, to theories, and also to laws. So straight off the bat, the first thing you're going to have to understand is the difference between an element, compound, and a mixture, and we're going to talk about that further on. And then what scientific models these are. So lots of scientists have carried out experiments 20 years ago, and we've learned things over time and developed these concepts further to develop essentially modern day chemistry. And we're going to, in the chemistry course, you're going to learn about all these models, and a lot of the time you're going to get exam questions where you have to recall what the initial theory was and how it's evolved over time. So, for example, the periodic table, of course, the latest model is that from Mendeleev, but we used to think that we could arrange elements as triads. So that's a very common exam question in GCSE chemistry, where you're expected to recall how models have developed and how theories have also developed. And also scientific laws as well, very important. So a very common example of this is when you're doing chemistry calculations. There's very standard chemistry laws that you're going to have to apply when making calculations. So, for example, knowing that a mole is equal to concentration times volume, and how to apply this to different concepts. And a very common way that examiners like to ask questions is in the context of a real life example. And this is when a lot of students tend to make mistakes in exams. Sometimes it's very easy to answer questions when they've given you the mole, given the concentration, given the volume, and it's just a simple case of doing the right calculations. But sometimes they give like a paragraph of background, and then you kind of have to piece out things and take out the important things and leave out the unimportant things in the question to reach the answer. And it's this process that a lot of students struggle with. But with every other thing, practice makes perfect. So the more you practice these kind of questions, the better you get at them. As students, you're going to learn about atomic theory, you're going to learn about elements, you're going to learn about compounds and also reactions as well. Atomic theory is very, very important. It's topic 1 of pretty much all GCSE syllabus. And chemistry is kind of unique to, say, biology, for example, because you're building on concepts over time. So you can't go further in chemistry knowledge to learn about exothermic reactions and endothermic reactions and activation energy if you haven't understood the basics of how atoms work. Whereas, say, in biology, you can know a lot about the digestive system and not know much about the nervous system, and still kind of get away with that in exams. Where with chemistry, you can't really do that because everything links to each other. So to understand the next bit, you need to know the previous bit. So it's really important that you're keeping on top of the modules and with the work on a weekly basis to make sure that you are able to build on those foundations or those concepts effectively throughout the year, and of course leading up to the exam as well. A key part is, of course, compounds, but also reactions. Reactions are a very, very big part of chemistry, and very early on in GCSE course, you're going to learn about how to write up a chemical equation and how to balance chemical equations as well. And it's really important that you understand these concepts because reactions can get quite complicated very quickly. And a common exam question the examiners like to ask is, they give you two reactants and they expect to come up with the product. So for a lot of reactions, you need to be able to remember the general chemical formula. So knowing that when an acid reacts with a metal, it usually produces salt and hydrogen. And they can just put any acid there. So they could put hydrochloric acid, and then reacting with magnesium, for example, and you're expected to know what the salt that will be produced, so magnesium chloride and also hydrogen. And they might then add an extra 1 mark question and say, what's the test for hydrogen? So it's really important that you understand how chemical reactions work, learn all of the general formulas that are necessary. And quite simply, if you don't learn the general formula, you're not just going to remember or just figure out that when an acid or a metal reacts, they make salt with hydrogen. So it's really important that you get on top of the knowledge as well. So yeah, chemistry is the structure of study of substances, their properties, their structure, and the changes that they undergo. I think this is a really nice kind of one sentence summary of what chemistry is about. Chemistry is the study of substances. It's pretty much everything, all the materials around us. How are they formed? How are they made? Are they made naturally? Are they made artificially? Is there specific conditions that are needed in order to make them? So if they need to be made under 100 atmospheres or 25 degrees or 100 degrees Celsius, is there a way we can make this faster? So catalysis, what is a catalyst? A catalyst is anything that speeds up reactions or makes them faster. And the Haber process is a classic example of this. And the Haber process is the process of making ammonia. And ammonia is very important, of course, especially in plants, because plants use ammonia to make nitrates. And we could actually make this process faster if we put iron in it. Iron is a transition metal and it's a catalyst for the Haber process. And it's the study of chemistry that allows this to happen. So now we can, make our crops grow faster because we know how to harness the Earth's kind of natural resources to make life easier for us. And what chemistry kind of really focuses on is more the artificial side of things. So if we're looking at how we make things out of a natural environment, then that's chemistry. If you're looking at it in a natural environment, that's biology in general. So there's that distinction there between biology and chemistry. Of course, there's some cross. So if we're looking at biochemistry, but in general, chemistry tends to be out of the natural environment context. And we're of course going to study the properties of these substances, and this could be their physical properties, or it could be their chemical properties. So physical properties, their melting point, their boiling point, their density, or chemical properties, what they react with, what their electron structure is, and what they look like, and so on and so forth. And also the structure as well. Structure is very important. And we are able to create models as well for structures. And when you go on to study chemistry at undergrad level, it's very important to be able to visualize these structures. So we have kind of 3D models that we use to visualize how we think two elements, for example, could react with each other, or two compounds could react with each other. And we have lots of different techniques of testing this as well. So, for example, NMR spectroscopy is very important. We're studying the structures of chemical molecules, especially like organic molecules, for example. NMR spectroscopy is very important for the study of organic molecules. In A-level course, you'd be expected to utilize this technique to decipher the structure of simple organic compounds. Mass spectroscopy is also very important. Chromatography. There's lots and lots and lots of different techniques that we use to study substances and work out their structure and test out how they react. There's tons and tons of them, and you start learning about them straight off from your GCSE course. You learn more in A-level course, and of course, if you decide to study chemistry undergrad level, you're going to learn much more. And also the study of the changes that they undergo is very important, because part of studying something is knowing how it reacts to change. Now we can anticipate this and exploit this for our own use as humans, also artificially. Um, I actually think that chemistry is the central science, because essentially it links all types of sciences, both social sciences and physical sciences together. So chemistry pulls together concepts from biology, pulls together manufacturing, very important. So, for example, margarine, how do you make margarine? From hydrogenation of unsaturated fats. So we make margarine. So it's really important for manufacturing. Geology, of course, looking at rocks and how they respond to change over time and what kind of chemical reactions they undergo as well. Economics, very important as well. And of course, medicine and engineering. So chemistry is that concept, or that branch of science that really pulls together all aspects of the sciences, and all of them take out concepts from chemistry, albeit at different amounts, but they all bring in chemistry to their concepts as well. So chemistry pulls everything together. So of course, like I mentioned before, chemistry is the study of substances, and we have pure substances and we have impure substances. It's very important to know this from your first time of studying chemistry. And in your first lesson, you're going to be learning about distinction between an element, a compound, and a mixture. So an element is made of only one type of atom. A compound is made of more than one, so at least two types of elements. And a mixture, difference between a compound and a mixture is that compounds are elements that are chemically combined together, whereas mixture, yes, it's made out of more than of at least two elements, but they're not chemically combined together. And a common error some students make is when they're looking at alloys. So alloys, for example, steel, which has got iron in it as well, is an alloy, and that's actually a mixture of two different metals to make an alloy. And we do this to make a stronger substance. So in general, alloys tend to be stronger than the pure metal, because the metal ions can't slide past each other as easily. So there's a bit more friction in that sense. So a lot of students tend to think that alloys are compounds, but they're actually mixtures. And when it comes to compounds, very important to know the distinction in different ways that you can make a compound. So what type of bonding is involved? So you could have ionic bonding, you could have metallic bonding, you also have covalent bonding as well. It's very important to know the distinction between these three types of bonds, and the relative strength as well. So covalent bonds are actually the strongest of the three. And a lot of students tend to kind of mistake the nature of the bonds. So covalent bonds is formed by the sharing of an electron pair, whereas with ionic bonding you get outright transfer of an electron, usually from the metal to the non-metal. So there's going to be charged particles formed from that reaction. So metals form positive charge and non-metals form a negative charge, and you can easily spot this from a periodic table. So if you've got a group 1 metal, sodium for example, and chlorine, which is a group 7 element, when they react to make NaCl, the octet rule is very important. That's what every element wants. You want a full outer shell. And to do this, sodium is going to have to transfer that one extra electron that it has to the chlorine, so that it has a full and new outer shell, and chlorine has also got a full outer shell as well, because it's gained that extra electron from sodium, so that it has 8 electrons on its outer shell. So it's really important to understand the octet rule, the basics. What does it mean for an element to be in a group? It means that if an element is in group 1, it has 1 electron in outer shell. If it's in group 2, it has 2 electrons on its outer shell, and so on and so forth. So to be able to understand how compounds are formed and understand why does sodium, transfer 1 electron to chlorine and not 2, you really need to understand the basics of periodic table. Periodic table is very important, and it's part of the data that gets given to you in exams. It's literally like you need to study it, and you're gonna look at it so much you're gonna remember a lot of the elements. And a good tip is that for the GCSE course, there's a kind of limited number of elements that they'd like to ask questions on, and the more you practice, the more you understand. So knowing what a group is, knowing what a period is, the difference between a non-metal and a metal, what's different about transition metals, why do you call them transition metals, why do they form colored compounds, whereas group 1 elements are just white or colorless. So it's really important with chemistry that you question the why. So that intellectual curiosity is really important, and that's what examiners like to see, which is why they design questions the way they do, to make sure that they're really testing your understanding of chemistry. And of course, metallic bonding is different kind of bonding between positively charged metal ion and delocalized electrons. So it's really important to understand the types of bonding, and of course intermolecular forces as well. So hydrogen bonding, dipole-dipole interactions, for example. Lots of students, sometimes it's a hit and miss in terms of understanding of these types of bonds, and a lot of students kind of mistake one for the other. Van der Waals interaction is also very important. It's intermolecular forces. They're also the weakest types of bonds as well, and they're not bonds to form a compound, they're just bonds between molecules. So understanding those key differences and the types of bonds or forces that are discussed in chemistry is really, really important. And with mixtures as well, they like to ask about separation techniques. So you probably would have done some of these experiments at school. So filtration, for example, if you want to separate sand from water, and if you want to separate salt from water, then heating and evaporation is the technique that you'd go for. If you want to separate ethanol from water, then you need to do distillation, because they're both liquids, but they have different boiling points, so you can heat them up to the point of their boiling point, and then condense one of the two, and then what you've got left behind in the flask is going to be the separated water from the ethanol. So it's really important to know the different separation techniques for mixtures and why we would choose to use the different ones in what context. And of course, say chromatography, you've probably done the classic kind of separation of ink, so different components of ink experiment. So there's lots and lots of things under elements, compounds, and mixtures. And sometimes it's easy to think that it's a pretty kind of straightforward subject, but there's lots of intricacies that examiners like to test in exam that students overlook. So it's really important that you understand and really study the differences between element, compound, and mixture, and the scientific models behind them. And of course, it's also important to look at the history of how our knowledge has evolved as well, because that's something that examiners like to ask about, and that's something that a lot of students miss out. They kind of learn about the scientific theory, the concepts, and they forget about how it came about in the first place. So it's important that you study this. This is a kind of more complicated kind of mind map diagram of chemistry. So looking at again elements, compound mixtures, and differences between pure substances and impure substances. So yeah, I recommend really kind of making sure that you understand the bit, because really this is the first topic. If you're looking to start learning chemistry, this is the first thing that you need to make sure that you have a grasp of. And because chemistry is one of those topics where you're building on the knowledge at but every lesson, it's not like biology where a lot of the time sometimes you can learn about something completely different unrelated to previous lesson. With chemistry, lots and lots of things linked together. If you don't understand elements, compounds and mixtures and all the theories behind them and how they're formed, then it's very difficult to then move forward to other topics in chemistry. So it's really important that you understand this. And of course they're built on at different levels in A levels versus GCSE. So in A levels, you kind of relearn everything that you've learned in GCSE, and also you add a whole load more to that. So you start learning about electron structures in GCSE chemistry, and so knowing that the first shell has 2 electrons maximum there, and in other shells it's 8. When you go to A-level chemistry, you learn about, atomic orbitals and hybridization, what's the difference between sp2 and sp3 hybridization, and so on and so forth. So there's always lots more to learn. If you learn chemistry on undergrad level, you learn about other types of subatomic particles that you've never heard about in GCSE and A levels. So there's more and more added layers, because we've kind of discovered more and more, and we're still discovering more, and as we add more, there's more to learn as well. Okay, so we've already discussed this. An element is a substance that cannot be broken down into anything simpler by chemical or physical change, because it only contains one kind of atom. So all the elements are listed on the periodic table. And a compound is a substance that contains 2 or more elements bonded together in fixed amounts. And there's also other concepts surrounding this, like empirical formula of a compound, so the basic kind of molecular form of a compound. So if you've got a compound that says C60 H20O6, what they can ask about is the empirical formula. And this is like a classic kind of calculation question that you get asked a lot, especially when it comes to organic chemistry. And of course, mixtures are made of substances that are not bonded together at all, and they can be easily separated, and their composition can also be changed easily. So I always recommend with chemistry to practice, and there's lots of resources out there. So a basic kind of activity is for you to spot which one's an element, which one's a compound, and which one's a mixture. And there's a kind of general list of most commonly discussed elements, compounds, mixtures at the GCSE level and also the A level So I recommend basically just learning these to start. Obviously there are going to be exceptions, but water, for example, you're probably gonna come across water multiple times in your course. Water is one of the most common molecules. It reacts with lots and lots of things. So knowing that H2O, that water is H2O, is important. It's made of 2 hydrogens and 1 oxygen, so it's compound because it's made of more than one type of atom. And then copper, if you look at the periodic table, you spot that copper is actually on the periodic table, and the fact that it's on there means that it's an element, because the periodic table is a list of all the elements that we know till date. And air is made of a mixture of gases. We have hydrogen in the air, we have nitrogen in the air, we have carbon dioxide in there, we have oxygen in the air and traces of other gases as well. So air is made up of lots and lots of gases, all in different proportions. And there's a topic at the end, kind of at the end of GCSE chemistry, called atmospheric chemistry, and that's where you really learn about why the percentages that we've got of different gases in the air is the way it is. So in present day, in modern day Earth, we have lots of nitrogen, and we don't have that much carbon dioxide. Whereas, hundreds of millions of years ago, we had lots of carbon dioxide and water vapor, and we had pretty much no oxygen. Whereas now we've got like 21% oxygen. So how did this come about? How did the present day atmosphere evolve? And that's a really, really interesting topic that they like to ask about as well. So. And there's also lots of documentaries as well out there if you want to learn a bit more. I think it's quite an interesting topic. And also oxygen, you find that oxygen is on the periodic table. Yes, it's made up of O2, but it's still the same oxygen. It's just a diatomic molecule. So they form covalent bonds. When you learn about the different types of bonding in detail, you find that oxygen has covalent bonding, so there's sharing of an electron pair between two oxygen atoms to make O2, because it gives them that full alpha shell. The only reason why compounds react is if they're getting the full alpha shell. Sorry, the only reason why elements react is because the reaction gives them a full alpha shell, makes them more stable. So if something is not favorable, it probably won't happen naturally. It definitely won't happen naturally. So you need to either put in energy or do something, or a catalyst to make that reaction happen. So pretty much everything in chemistry, all the changes that elements and compounds undergo is because they're more stable at the end of it. Stability is a very important kind of thermodynamic concept, because that's what everything is working towards. Everything is working towards stability, and it's going to react to other things to get there. And when you understand the key kind of underlying concept of chemistry, suddenly a lot of things kind of make a lot of sense. So you understand why maybe we need to put a bit more effort to make an endothermic reaction work, whereas exothermic reactions, it's spontaneous. And of course, carbon dioxide is also a compound. It's CO2, so it's got one carbon and two oxygen molecules. And concrete is a mixture, as you can tell, it's not in the periodic table and it's not a compound. And chlorine can be spotted on the periodic table in group 7, so it's an element. And copper sulfate is a compound, and kind of gives it away because it's got copper and it's got sulfate. Sulfate is SO4, so it's made up of sulfur and also 4 oxygen elements. And here are the answers. So I talked a little bit about models before, but models are very, very, very important for us to understand chemistry and visualize things, which really helps us to understand the concepts behind reactions and why they happen the way they do. So, for example, bonding, metallic bonding, covalent bonding, ionic bonding, we like to use dot and cross diagrams a lot to represent bonding and electron pairs. When we're drawing exothermic reactions, we draw an energy diagram to show, the activation energy and what happens reaching that transition state, and what happens with energy levels in the reactants versus the products. So presenting things in pictorial form is very, very important. And also gets you extra marks in the exam as well. Examiners like to see diagrams. You're illustrating things with diagrams. So if you're talking about a compound being formed by covalent bonding, they want to see the electron structure. They want to see what's sharing electrons with what. Where are the lone pair of electrons, or where are the free electrons? If you're describing metallic bonding, they want to see a diagram. They want to know where is the positively charged ions, where are the delocalized electrons. So yeah, this is really, it's very, very important to have models because it attracts higher marks. And a common mistake that lots of students make is they describe chemistry in words, sentences, paragraph essays, but with no diagrams. And you need diagrams to attract the highest marks. Sometimes the examiner will be explicit and ask that you illustrate a point with a diagram, and sometimes they're not, and they just give it 6 marks. But best believe two or three of those marks are for drawing diagrams. So it's up to you to make sure that you draw those diagrams so that the examiner understands, so that you show the examiner that you understand the concept. So here's an example. So elements made of only one type of atom, and compounds are made of 2 or more types of atoms bonded together. So all this time I've kind of been describing them and talk about them in words, but the moment you put a diagram to it, all of a sudden it makes it easier to remember as well, because now you can see a difference, not just talk about a difference or write about a difference between an element and a compound. You can see that you've got 2 different things joined together, and here you've got 2 different things joined together, whereas the element, it's just the same circle and just the same triangle. And that's something that you won't, that's just illustrated best when you draw diagrams. So even organic chemistry, for example, when you're talking about reactions, really important, draw diagrams, use curly arrows to show the movement of electrons, so that the examiner understands, so that the examiner knows that you understand how you got from the reactant to the product. What are the intermediary steps in that reaction that led to the product? The best way of illustrating this is through diagrams, through curly arrows. So always draw diagrams whenever you can, because you're attracting the highest marks. And of course, mixtures contain elements or compounds that are not chemically combined together. And you can see this very easily. Here you've got an element, you've got a compound, you've got a compound, you've got an element, and something similar here, but they're not bonded together at all. They're free moving, they can do what they want. So there's no chemical bond between the different elements and compounds and mixtures. So here's an activity that you can do to test out your knowledge. So you've got the key, where carbon is a black circle, hydrogen is a square, and oxygen is a white circle. And you can draw picture models to illustrate the differences between the element carbon, so just its own, compound carbon dioxide, so you're going to join 2 oxygens and also 1 carbon. And then carbon monoxide, which is made up of 1 carbon atom joined together with 1 oxygen atom, so you just put in 1 black and 1 white. And then a compound water, so you put in the square, two of those, because water is H2O, and also a central oxygen atom. And then finally you've got the mixture of all 3 substances. So you've got carbon, carbon dioxide, carbon monoxide, and water, not chemically combined together, and just kind of free flowing. So yeah, it's very important to use picture models or pictorial formats to illustrate key concepts in chemistry, because it shows the examiner in the easiest way possible that you understand the concept. And we talked about molecules a bit already. So most elements are made up of individual atoms, but some elements exist as molecules. So we talked about O2 as a diatomic molecule. It's still an element because it's only made up of 1 type of atom. Again, you can illustrate this with diagrams as well. Some elements exist as molecules, and an example is hydrogen. I mentioned oxygen, but you've also got nitrogen. You've got sulfur as well, which is SA. Sulfur, molecular sulfur is not something that's seen as much in the GCSE course, but you're going to be seeing nitrogen, oxygen, hydrogen a lot, well, especially when it comes to organic chemistry. They're very, very common elements to discuss. And understanding the periodic table is, of course, very, very important. Know where things are, know how it's structured, know the theory behind it. For example, why did Mendeleev leave gaps in his initial model of the periodic table? And know what group is, know what a period is, what is a noble gas, why are they so stable, why are they so unreactive, what is a transition metal, why do they form colors, why can they have multiple charges, why can we see iron as Fe2 plus or Fe3 plus, whereas with sodium we only ever see it as Na plus, and with magnesium we only ever see it as Mg2 plus. It's really important that you ask all those questions. Why is carbon bonded to 4 things? Again, the periodic table is going to really help you answer this question. And the good thing is you've got a copy of the periodic table that's in your exam that you can use, so you don't need to kind of memorize where everything is. But over time you will find that as you do more and more practice questions with chemistry, you're going to know where a lot of things are, especially the most commonly talked about elements in the course. And there are also 7 diatomic molecules, so HNOF, so hydrogen, nitrogen, oxygen, fluorine, Cl, bromine, and iodine. And an easy way of remembering this is using the sentence, help our needy class find brains immediately. So the first letter represents each of the elements. I definitely recommend finding ways of easy ways of remembering specific chemistry concepts. Is what I did a lot when I was studying chemistry as well back in GCSE and A level, to make sure that you're remembering the concept as accurately as possible. And there's lots of different ways that you can do this as well. So this is where study techniques come in. Very important for you to organize the concept well. And yeah, we've pretty much talked about the key parts of the periodic table. And of course, when you start learning chemistry, you're going to learn a lot about it in more detail. You're going to find that they like to ask you to compare elements from different groups a lot, and looking at reactivity and why things react, or how reactivity changes as you go down the group, whether it increases or decreases, and why this is. So with every concept in science, pretty much, it's more important to know the why than to know what it is. So they're always going to be asking you about the why. So with everything that you're learning throughout the course, make sure you're asking yourself why, because that's something that they want to know. That's what gets you the marks. You're probably going to get 2 marks or maybe 1 mark by saying what's happened, but then there's going to be a lot more marks for being able to understand, to describe the scientific process or the scientific understanding behind what has actually happened. Yeah, there's lots of different ways of kind of practicing your knowledge of the periodic table. There's quizzes, there's lots of worksheets out there, and I recommend doing as many practice questions as possible, especially also when it comes to the mathematical concepts of chemistry, so like molar calculations and that kind of stuff. I think it's really important to get as much practice as you can. And say in a mass spectroscopy, so deciphering the structure of simple organic molecules, the more practice you do, the better you get at it. And also mass spectroscopy as well, they like to combine different techniques a lot, and then ask you to decipher the structure of the molecules. So the more practice, it's kind of like maths, the more practice you do, well, it is pretty much maths because you are doing mathematical calculations. The more practice you do,